Last time we described the laser system uh, by using a mirror and laser material and another mirror at the other end. Uh, Laser operation starts by supplying pumping to the medium. And pumping process, I explained that is uh, pumping the ground state atom to the excited state of the atom. And by using the spontaneous emission and stimulated emission, we can make the laser operate at a given wavelength. And today we'll discuss about the pumping process and the spontaneous and stimulated emission and relaxation oscillation and Q switching. Those are the process related to the pumping and the emission of light to the surrounding medium. To describe this, we need to first describe the absorption process of the medium and interaction of the medium to the surrounding light intensity. So the topic of today's course is absorption by classical driven harmonic oscillator model. The atomic model absorption of the process can be explained by simple harmonic oscillator. It can be modeled with a positive nucleus and the negative electron staying in a equilibrium position. If there is a external electric field existing nearby this atom, then because of the oscillatory electric field of the external field, atoms start oscillating around its equilibrium position. And this external oscillation can be explained by a damped harmonic oscillator model. This is a classical model of an atom interacting with the external field. So we can define the force acting on the electron nearby a positive nucleus by using this equation. External force acting on an electron can be described by the external force plus the damping force, which acts as a damping term, and there is a restoring force. And with the Newton's equation, we have F is equal to ma. A is acceleration, so Q double dot is the acceleration. And here Q is defined as the displacement of electron from its equilibrium position. So, for example, this is when Q is 0, and when electron is displaced from its equilibrium position, then we define the distance of the displacement of electron as Q. So Q is the displacement from its equilibrium position. And we defined the restoring force with the quadratic harmonic potential. If K is a spring constant, then we can define V restoring potential with 1/2 kq squared. Or we define this as the 1/2 m capital omega squared times small q squared. This capital omega is the resonant frequency of the electron, bounded electron. And the external force is just minus E times external field, so we define external field as E0 over 2 exponential minus I omega t plus exponential plus I omega t, which is basically a cosine omega t function. So by putting external force with this form and restoring potential with this into the equation 1, we have minus E, right? If we rewrite equation 1 with respect to this Q, we can rewrite equation 1 as minus E times capital ET is equal to mq double dot plus m gamma times q dot plus m capital omega square times q square. And then this becomes equation 2 by putting the external force term and into this equation. Then this equation 2 is a simple second order differential equation, which is the q double dot plus gamma times q dot plus capital omega square q square is equal to cosine omega t function. Then we assume the solution of equation 2 as qt is equal to capital Q over 2 times exponential I omega t plus exponential plus I omega t. By assuming this solution and putting this to equation 2, we have on the left side we have capital omega square minus small omega square minus I gamma omega times capital Q omega is equal to minus E times capital E over M. By eliminating exponential minus I omega t plus exponential plus I omega t on both sides. Then capital Q as a function of omega can be written as minus E times capital E0 over M 1 over capital omega square minus small omega square minus I gamma omega. And if we rewrite this with the real and imaginary term, we can rewrite this capital Q with this equation 3. And so equation 3 is the solution of differential equation given as the equation 1. So as we have this solution, we write the polarization P as a function of time as minus NEQT. Q is the displacement of single atom, E is the electrical charge for the electron, and N is the number of atoms per volume. And that's the definition of polarization. So by using the atomic constant E, small e, and the number of atoms per volume N, we can represent the polarization like this equation, like equation 4. As we have already solved the q as a function of t in equation 3. Q is capital Q omega over 2 times the exponential terms like this, and we have already solved the capital Q, so we have solution for small qt, and putting small qt into this equation, we have the expression for the p0 as a function of omega, which is capital N times E square times E0 over M 1 over capital omega square minus small omega square minus I gamma omega. Sorry, 0 is the misprint here. And we can rewrite this complex term to have this form. Right. And in electromagnetic theory, we have polarization equal to external field E0 times the epsilon times chi. So with this definition, we can define the chi as a function of omega with this atomic constant n E square over epsilon 0 m 1 over capital omega square minus small omega square minus I gamma omega. Right. So we have the expression for chi. Chi is the macroscopic parameter of the medium, and large N or small e and capital omega and gamma are the parameters for single atom. So we have related the chi, it is a macroscopic parameter of a medium, with the atomic parameters with equation 7. Next step is to express the chi with the refractive index and absorption coefficient, which is a well-known parameter for a optical medium. So in order to relate the chi with the refractive index and absorption coefficient, we need to relate this by using the wave equation. This is a review, and we like to derive the wave equation from the Maxwell's equation. So Maxwell's equation without any charge term, external charge term, can be written as equation 11, 12, 13, and 14. So just follow this process. The equation 14 is when J, the external current term, is 0, we can rewrite this equation into equation 14. Then by taking curl of equation 13, sorry, not 3, 13, left side we have curl of E, and right side we have round over round T times curl of B, and right. And the left side curl of E can be rewritten with equation 15 by the vector identity, and curl of B in equation 13 is can be replaced with equation 14, because curl of B is related to round D over round T. So we replace this color B with the D field by using equation 16. And then by putting 15 and 16 into 13, sorry, this is still 3, this is misprint. And then we have equation only for D and E field, equation 17. And when we have a uniform medium, when there is no boundary, we have divergence E equals 0, so we can simplify equation 17 or even further. And then we have left side of 17 just minus del square times E, and right side is the round square over round T square times D. And D is nothing but the D is P epsilon. D is epsilon 0 E times P, so we just replace D with the epsilon 0 E times P plus T P. So we have simplified equation 17 even further to del square E minus 1 over C square, round square over round T square. E is equal to mu 0 round square over round T square times P. And for a simple one-dimensional case, for a plane wave propagation, we can simplify this vector equation into the scalar equation with just one-dimensional case. And we just replace Et as E0 over T exponential minus I omega T plus exponential plus I omega T. And same is true for P, like this. And as P is related to E with epsilon 0 times chi E chi, we can replace equation 17 with this new equation. It is for one-dimensional case, del square is replaced with round square over round Z square, and the other part is replaced with the with these two terms. We have minus omega square over C square 1 plus chi times E0. And right. And this is another differential equation, which is the second derivative of this E0 is minus times constant times E0. So we just assume that the E0 is sorry, this is the error. We can just replace this as E0 tilde times exponential I kappa Z, where kappa is K plus I alpha over 2. This is just a definition. Kappa is the constant we need to find from equation 17. By assuming this solution, as the equation, differential equation is nothing but the second derivative of a function becomes itself. So we can assume the solution is exponential function I kappa Z, and this is the to have a physical meaning, we need to replace substitute kappa as K plus I alpha over 2. And then by putting this assumed solution to equation 17, we have left side this, right side this one. Then there are imaginary part and real part. So by making this imaginary part and the real part separated, we have n square k0 square minus alpha square over 4 is k0 square 1 plus the real part of chi, and the imaginary part of this equation is the n times alpha is k0 imaginary part of chi. So we have n square minus c square times alpha square over 4 omega square is equal to 1 plus real part of chi, and the other equation is n times alpha is omega over c imaginary part of chi. So we have these two relations. It relates the chi and refractive index and absorption coefficient. Here k and the alpha has the physical meaning for a plane wave. K is propagation constant and alpha is the absorption coefficient of a plane wave. So we have related the refractive index and absorption coefficient with the real and imaginary part of chi, and chi we have already the solution, not solution, the expression with the atomic parameters of the medium. So the final conclusion of this PPT file is can be summarized with these three equations actually. Chi is related to the atomic constant with equation 7, and the refractive index and absorption coefficient of the medium is related again to chi, imaginary and real part of chi, with these two equations. So these three equations are the major part we need to have, and we'll need these three equations to describe the interaction between atom and the external electromagnetic wave, photons. And here is the homework. Homework is to solve the following equations. These are the three equations: n square and alpha square relation to the real part of chi and the imaginary of chi, and the chi has the expression with the atomic constant like this. And when the n times e square over epsilon 0 times n is 10 to the 30, this is the unit is this is second 1 over second square, and capital omega is 6 times 10 to the 14 inverse second. The gamma is 10 to the 13 second inverse seconds unit. And when these three constants are given, you need to calculate these three equations and plot the refractive index and absorption coefficient for lambda starting from 0.1 micron to 1.5 micron. So we have the refractive index spectrum and absorption spectrum for a medium whose atomic parameters are given with these three numbers. As you can see that the capital omega is the resonant frequency. This is 6 times 10 to the 14, so the resonant wavelength lambda 0 is 500 nanometer. You can find that from capital omega. And the gamma is the damping term of the simple harmonic damped simple harmonic oscillator model, and this determines the width of the absorption spectrum, and you will find that by solving this one. And this constant determines how large is the absorption and the absorption peak. So you can, by using this, you can relate the refractive index of absorption and absorption coefficient. And in the previous lecture, I explained that the stimulated emission is related to the absorption, and we just derived the absorption coefficient by using, so absorption coefficient alpha is related to chi, and chi is related to the atomic constant like this. It can be represented by the number of atoms per volume, and the resonant frequency or resonant peak of the medium, and gamma is the absorption width, spectral width of the absorption. So by having that numerical expression for the absorption coefficient, we'll discuss about stimulated emission process and the mathematical expression for the stimulated emission, and then we'll start describing the interaction of the laser medium with the oscillating electric field, which is basically the dynamics of laser, and those are the topics we need to cover in the future, which is related to the relaxation oscillation and Q switching of a laser. That's about the course, and the homework is due in 1 week. So next Friday is the due, and you need to submit it through the YSEC. Thank you.